So we'll continue on, and so last one was in terms of exponential functions, so today the opposite, being in terms of logarithmic functions. So for example, in terms of basic graph, and we'll look at y equals log base 10 of x. Normally when you're doing log base 10, you will not see the 10 down here, so we'll get rid of that. If it's any other base log, you'll see a number in that spot. So, for example, plug in some numbers. And so 1, 100. And so the log of 1 is 0. The log of 10 is 1, and the log of 100 is 2. And so if we start to put this on a graph, we end up with something like this. So log of 1 is 0, 10 is 1, and so we end up with a curve that is slightly increasing. So if I go way out there, eventually we'll be out to 100. Right? And then if I go to numbers that are less than 1, so point 0.1, 0.01, 0.001. So 0.1 would be -1, 0.01 is -2, and 0.03 is -3. And so this curve continues on and goes down like that. Right? And you cannot take the log of a negative number. So we have in terms of our basic log graph, right? And then if you remember in terms of the last week, we had in terms of exponential graphs. And my basic exponential graph looks like this, right? And so if this is my graph, y equals 10 to the x. And so here the domain, you can plug in any number you want for x, so the domain was all reals. And the range, the numbers you got out, were numbers that were greater than 0. Right? And if I look in terms of my log graph here, right, well, my domain, the numbers I can plug in, are numbers greater than 0. And the range are all real numbers. Right? And so these are inverses of each other. Right? And so we have in terms of domain and range of our exponential and our logarithmic function. Okay? Okay. Well, just like we saw in terms of last week, we could then take our graph and we can move it around. And so if I have something like this, it works the same way as it did with our exponential, in that this number out here is your up and down. This number, which is part of this functionality, is in terms of your left and right. So if we graph this, and all I'm going to worry about is where is this one point? Where did this go? Okay? And once I know where that goes, I know what this curve looks like. So this x plus 2, well, again, we want to know when will that be. That is going to be our left and right. And so like we said last week, it's sort of opposite of what you would think. And so that is going to take this point, which was here, and move it over here, 2 point. It takes the asymptote line, which was here, and moves that over 2 point. And actually, our dot won't be here. Let's get rid of that, because we're going to also be moving this. So we moved it over here, and then the plus 3 is going to take that and it's going to move it up 3 units. And so we have that our curve is going to look something like that. Right? So we can move it in terms of up and down, left and right, the same as we did in terms of with exponentials, and it works the same way. Okay, on your calculator, if I say to find the log of some number, you could plug that in on your calculator and you will get an answer. Right? You can also, on your calculator, do this on the calculator and you can get a number. Those are the two that are built into the toy. This is log base 10. This is log base E. Right? But we can also do logs of other bases. Right? So, for example, let's say I want to know, well, what is the log base 3 of 75? Right? Well, let's see. I know that 3 squared is 9. 3 cubed is 27. And 3 to the 4th is 81. Right? So I know that this has to be some number in between 3 and 4. Right? And so the way I can get the answer to this is called by making use of what's called the change of base formula. And so I would have, the way I do this, it would be the log of 75 divided by the log of 3. And if you plug that into the calculator, you'll end up, this number comes up to be 3.9299. That's what he said, it has to be between 3 and 4. And if you then did this on the calculator, 3 raised to the 3.9299, you would end up with 74.996 and so on. So we get fairly close to what we wanted. Right? So we get to figure out the log base whatever. Okay, so again, we take the log of this divided by that number. So general, you think in terms of this as being log base B of m. The way I do this is you do the log of m divided by the log of b. Okay? And that'll give you whatever that exponent is. Right. So then, for example, if I want to do the log base 8 of 2, 3, 7, 8, 0, I want to get what that number is. So we take the log of 2, 3, 7, 8, 0, divide that by the log of 8, and we end up with 4.8458. I would also get the same answer if I did it by using natural logs. So either way, I'll get the same value for that answer. Right? So whether you do log or natural log, you'll still get to the same number. Well, in terms of logarithmic equations, right? So, for example, you have in terms of this equation, so this has to do in terms of audio and decibel levels. Right? I naught is the initial intensity, so the threshold of hearing, which is 10 to the 12 watts. Right? And so I want to know what is the dB level if I is given to be 0.15 watts. Right? And so we got the decibel level will be given 10 log 0.15 by 1 times 10 to the minus 12. And you plug that in, and this will come out to 112 So I got it in terms of a logarithmic equation. Right? And you see a few of those in terms of audio, with decimal levels. Well, in terms of logarithms, you get in terms of various properties of logarithms. And so the first property being the product rule. And so you get the log base b of m times n is equal to the log base b of m plus the log base b of n. Right? Now, a lot of these rules now, given that everybody has the toy, the calculator, is you can basically on a calculator plug in any number you want and get the value for the logarithm. Okay? But back not that long ago, you used to have tables in the back of the math books, and you had to look things up. And obviously, you couldn't print the tables that go out for every number, and so you had to know these things. But in terms of how this works, for example, so let's say I want to find the log of 15. Right? Well, I know that 15 is the same as 3 times 5. And so the log of 3, if you do this, is going to be 0.4771. The log of 5 is 0.6989. And if you add these up, you get 1.170. And if you do directly on the toy, the log of 15, you get that number. Right? So not very helpful in terms of now actually getting the log of a number, but these rules do come in handy when I want to solve for an unknown. I'll have to make use of these, and we'll see that a bit later. Right? So product rule. Right? So the next one then is the quotient rule. And so the log base b of m over n is given by the log base b of m minus the log base b. So if you think in terms of what we just did, we did 15 divided by 5, which is 3. If I took those numbers I had in the previous page and did a subtraction, and I find out, I would get that as the number. And then the last rule is the power rule. And so the log base b of m raised to the p is equal to p times the log base b of n. Right? So for example, 2 cubed I know is 8. Right? Well, the log of 2 is 0.3010. The log of 8 is 0.9030. So, if I take this number and multiply it by 3, I get that number. Okay. So we have in terms of those 3 rules, right? And we'll make use of those in terms of solving for an unknown. And then the other thing you need to know is that we had last week in terms of this is the exponential form. And then you need to be able to convert back and forth between exponential and logarithmic form. And so log base b of y is x. This is the logarithmic form. So for example, given that this is the exponential, y equals 3 to the 4th, and actually now y, let's see, that's going to be 81, right? And as I rewrite that in logarithmic form, this would be log base 3 of 81 is 4 And then conversely, given the log form, so if I said the log base 7 of 3, 5, 9, 6 is equal to x, and I say, okay, rewrite that in terms of the exponential form, then this would be 7 to the x equals 3, 5, 9, 6. Okay? So I need to be able to convert back and forth between the two forms. Okay? Other thing that we need in order to solve for an unknown are in terms of these two statements. And that is, if A is equal to B, then the log of A is equal to the log of B. Right? And then also if the log of A is equal to the log of B, then A has to equal B. So we have in terms of those things we're going to make use of in terms of solving for x, right? Other things we need to be able to do is in terms of what's called expanding a logarithm. So given something like this, log base 3 of x plus 2 cubed times x minus 4 over x minus 7 to the 5th times x plus 9 squared. So we're going to expand that all out. Right? And so the way we do this is everything on the top will be to the left of my subtraction sign, everything to the right will be on the right, because after all this fraction bar corresponds to subtraction. And so if I write this out, right, so we got log base 3 of the x plus 2, and then by the power rule, this 3 comes out front. This is multiplying, so we get the plus. And then we get the log base 3 of x minus 4. So that's everything on the top. The fraction bar corresponds to the minus. And now we'll do our bottom terms. So we get log base 3 of the x minus 7. And then the 5 comes out front, minus the log base 3 of the x plus 9, and then the 2 comes out front, and we have expanded that all up. Okay. So we got in terms of expanding the logarithm. And then being able to do this in the other direction, and that is to write as a single logarithm. So you have given something like this, 2 log base 5 x plus 9 plus 3 log base 5 x minus 7. So that part minus 9 log base 5 x plus 10 plus plus 6 log base 5 x minus. Okay. So we're going to write that as a single logarithm. So we know it's going to be log 5. The minus means we got our fraction bar here. And then basically everything on this side goes on the top. Everything on this side goes on the bottom. And so we got the x plus 9. That's going to be squared because that number up front. And then we get the x minus 7. That term is going to be cubed over my x plus 10. That number to the 9. And then the x minus 3. And that raised to the 6th power. And we have rewritten that as a single logarithm. So now we want to do this in terms of actually solving for the unknown. So we want to solve for x. So we'll go through a few examples as to how this works. So for example, I have 5 raised to the 2x plus 9 is equal to 8 raised to the 3x. And I want to solve it. Well, we want to get to our x, which is in terms of our exponent. And so the way we get to exponents is by doing logarithms. And so we'll do log on both sides. Okay? And when we do log on both sides, by our power rule, these exponents can then come out front. And so we'll get 2x plus 9 times the log of 5 is going to equal 3x plus 12 times the log of 8. Well, log of 5 and log of 8 are just some numerical value, and so we get 2x plus 9, and the log of 5 is rounded to be 0.6990, and then the log of 8 is 0.9031. And so now it's a matter of doing some algebra and solving this. So by multiply by our 0.6990, we get 1.38, 1.398, sorry, 1.398x plus 6.291 is going to equal 2.7093x plus 10.3837. So now we want to get the x's on one side, and so we'll take this one and we'll bring this over here. So we'll subtract 1.398x minus 1.398x. And so we'll have 6.9291 is going to equal 1.3113x plus 8372. Right? Next step is to bring the 10 over to the other side, and so we'll subtract that. Subtract this number, and subtract this number. And so we do that. Negative 4.5462 equals 1.3113x. And then lastly, we're going to divide. And we end up that x is going to be a negative 3.466. So we got x as a negative number. Now the thing is, we got to make sure is that the number is still valid. Okay. So again, we were as an exponential. We can do x can be any number, so we'll be good. When we do get to when we're doing logarithms and we're solving we do have to check and make sure we don't end up with a log of something we can't take. Right? So let's look at another example of this. So log base 3 of x minus 4 minus the log base 3 of 5 equals log base 3 of x plus 2 minus log base 3 of 7. So the first thing you want to do is rewrite each side as a single logarithm. So this is going to be the log base 3 of x minus 4 over 5 equals the log base 3 of x plus 2 over 7. Right, so we get that. Right. Well, we had earlier in terms of the statement that said if the log of A is equal to the log of B, then A has to equal B. So then x minus 4 over 5 has to equal x plus 2 over 7. Right? And so we want to now solve this. Right? And so we can do in terms of this proportion, so cross multiply. So we get 7 times x minus 4 is going to equal 5 times the x plus 2. So this will give us 7x minus 28 equals 5x plus 10. Right? We want to get the x's on one side. So we'll subtract 5x, subtract 5x, and so 2x minus 28 equals 10. We then are going to add 28. And so 2x equals 38. And then divide by 2. And x is going to be 19. So x is 19. Now we have to make sure that is truly a valid answer. And so if I go back to the original equation and say, okay, if I plug in 19 in here, well, this will be 19 minus 4. That's a positive number. That's fine. This will be 19 plus 2. That's a positive number, so it's valid. Right? So we do need to check and make sure when we're doing logarithm equations that it does not violate. We're going to try to take a log of a negative number. Right? Well, how about if I have one that is in terms of this? E to the 2x equals 20. Right? Well, if we have an E equation, we have to use natural log. The natural log and E are opposite of each other. So we do the natural log of both sides. And again, power rule, this will still come out front. And so we get 2x. And natural log and E actually end up canceling each other, so this will just become out into be 2x, is going to equal the natural log of 20. Right? So the natural log of E is just 1. And so we'll end up with 2x equals the natural log of 20. Next step is to divide by 2. And so we end up that x is going to be 1.498. So another one involving in natural log. So let's say we got 6 natural log of 4x is equal to 6. Now, well, this says 6 times, so the first thing we want to do is get rid of that 6 so we can divide. So we'll divide by 6, divide by 6. And so the natural log of 4x is going to equal 10. The opposite of natural log is E, and so here we're going to actually do E down here. Right? So E to the natural log of 4x is just 4x. It's going to equal E to the 10th. And then we're going to divide that number by 4. Okay. so if you do e to the 10th divided by 4, you end up that x is going to be 5506.6. Other examples then. So again, we're solving for x. So log base 3 of x minus the log base 3, x plus 5 is equal to. So this side we can rewrite as a single logarithm. So this is going to be the log base 3 of x over x plus 5. Okay. And now we want to go from the log form and rearrange it to the exponential form. And so this will be that x over x plus 5 is going to equal 3 to the 5th. And so this will be x over x plus 5. 3 to the 5th power is 243. The opposite of dividing is to multiply. So we multiply everything by the x plus 5. So this and this will go away. So we get x is going to equal 243 times x plus 5. And then keep on working this in terms of solving this problem. And so we'll get x is going to equal 243x plus 1, 2, and 5. And we'll get the x's on one side. So we'll bring this over. Negative 242x equals. And then lastly, we'll divide. And so negative 242. And so x, in this case, is going to be a negative 5.02. Okay. Again, we started out this as being a logarithmic problem. Okay? And so the question is, we got an answer, but is that truly a valid answer? Well, if I go back to the original, we find out we got a problem, right? Because if I plug in negative 5, I cannot do that here, and I actually cannot do that over there. So by rearranging it, we do change it into something we can solve, but given that this was a logarithmic equation to start with, we end up with an answer that is not valid. Right? So there is no answer to this particular problem. Right? Other types. Something like this, e to 2x minus 5e to the x plus 6 equals 0. Right? We're going to solve that one. Right? Well, it sort of looks like a quadratic, and it's very similar to a quadratic. It's actually quite similar to this quadratic. Right? And this one we know how to solve. It's factorable. So if I factor this, we're going to get an x and an x. Right? We got that the 6 is positive, the middle term is negative, which means both of these have to be negative. And then we needed two numbers, multiply together, give you 6, and have a total of 5. And so that'll be 2 and 3. And then we would say that either x minus 2 equals 0, or the x minus 3 equals 0. And so here we could add 2. Over here we would add 3. And we get our two answers, x equals 2 and x equals 3. Right? Well, this one factors basically the same way. The way you tell it sort of looks like quadratic is here we go from x to 2x. So my exponent doubles. Here we went from 1 to 2. And so this basically factors the same way. So instead of x and x, we're actually going to have e to the x and e to the x, and then a minus and a minus, and it'll be the same two numbers, 2 and 3. Okay. So we got e to the x minus 2 equals 0, or e to the x minus 3 equals 0. And then we can bring the 2 and 3 to the other side. And so e to the x equals 2. The color, e to the x. So e to the x is equal to 2, or e to the x. And then the way we get rid of the e is by doing natural log. And we have to do that on both sides. And so x is going to equal the natural log of 2, or x is going to equal the natural log of 3. Okay? So we get our two answers, and then we can get the appropriate decimal for that. Right? Okay. All right. One more type, and we saw in terms of our exponential growth equation from last time that a sub t equals a naught e to the k t. So we can look in terms of this one, right? And we played with this before, okay? And so if the initial population is 200, and grows to 500, in 10 days, how many will be present after 25 days? And we saw this in terms of last time. So we know a naught is 200. A10 is 500. And a sub 25 is what we want to find. Okay. So we said we could take the first set of information and find out our rate of growth. So we have 500 equals 200 e to the 10k. Okay. We're going to solve for k, so we're going to divide by 200, divide by 200, so 2.5 equals e to the 10k. Again, opposite of e is natural log, so natural log of both sides. So the natural log of 2.5 equals 10k, and then lastly divide by 10. And so we divide this by 10, divide that by 10, and we find out that our k value in this case is 0.092. And then, like we did last week, we can now answer the question. And so a sub 25 equals 200 e 0.092 times 25. And we plug that in, we round that to the nearest whole number, and we get 1,995. And that will conclude